Here's part 3, and that's determination of empirical formula, right, by titration. Okay, by titration. So since we're using EDTA and we're using copper, right? Just so you know, EDTA stands for ethylene diamine tetraacetic acid, right? And when you mix that with copper chloride, right? And I'll just put the copper part here because that's all we really care about. That's what's going to interact with. You get EDTA doing what we call complexing or chelating copper in a rate of at a ratio of 1 to 1. So for every molecule of EDTA there's going to be one copper atom, right? Uh, and and so EDTA is this molecule that has 4 arms on it. That's why it's tetraacetic acid. And these 4 arms will actually grab onto any metal, right? So in this case, it's copper, and it will hold a single copper atom in its arms, in its 4 arms, right? So that means we have a 1 to 1 molar ratio. Okay. So in this case, uh, instead of having an acid-base titration, right, we're doing an EDTA copper titration. And so the thing that's being titrated is going to be the copper. Okay, I don't know why I wrote copper twice there. I meant this is the titrated. And in this, the EDTA will be the titrant. Okay, right. So previously, when we were talking about acids and bases, acid-base titration, right, the titrant was always the base, and the titrated was the acid, right? Well, in this case, the acid EDTA, right, is the titrant, and then the copper is the titrated, right? So what that means then is that when you have your burette, like so, and here's my stopcock right here, and then my little stopcock knob, and then my little spout, right? And then I have my little flask down here to catch the titrant. Okay. And so what's going to go up here? What's going to go in here is going to be the EDTA, right? Because it's a titrant, right? And in this example, we'll say that the EDTA's concentration, right, is 1.9. Oh, sorry, not 1.9, 0.19 molar. Okay, 0.19 molar. So we'll fill it up, and just like before, since we're using a new solution right now, if I were you, just to make my life easier, I would just put it so that it's at the 0 milliliter mark, right? And then down here, in some water, we're going to dissolve some copper chloride. Okay, we're going to dissolve some copper chloride. And we're going to dissolve, say, 0.142 grams of copper chloride. Okay? And in this case, we don't care about what the volume of water is because all we care about is the number of moles of copper chloride, and we can figure that out just from the EDTA, right? And so one of the reasons why we do this kind of experiment is because sometimes we're not sure what type of copper, right, uh, is actually combined with the chloride, right? Because there's actually 2 types of copper. There's copper 1, all right, and there's also copper 2. Okay, so copper 1 has a charge of +1, whereas copper 2 has a charge of +2. And so if you wanted to make copper 1 chloride, all you would need then is a single extra chloride because chloride has a -1 charge, right? So a -1 plus a +1 makes a 0, right? So that's going to be copper 1 chloride. But if you had copper 2, you'd actually have two. You would need 2 chlorides to actually make a neutral compound, right? So it's actually 2 times -1. That way you get -2 here, balances out a +2 on the copper 2 side, right? So, and I honestly don't know, whenever you're doing an experiment, I don't know whether or not the instructor gave you copper 1 chloride or copper 2 chloride. You just have to go through the titration and figure out which one you got, right? And so the question is, which kind of copper chloride do you have? Do you have copper 1 chloride or do you have copper 2 chloride, right? And this is how you figure it out. So I forget again what the indicator is that you put in to do this kind of titration. I think it's like Miri-X or something like that. Miri-X, and I'll just kind of trail off the end there since I don't know what it actually is, but it's something that sounds like that. And of course, 2 drops of that. Don't forget to put in those 2 drops because you'll keep on doing the EDTA and nothing will ever happen, right? And so we'll let the EDTA drop down into our copper chloride solution, right, until it turns, I believe this indicator turns yellow. I believe this indicator turns yellow, and yellow or orange, I can't remember. But let's see here. Yeah, I can't remember if it's orange or yellow. But when it does get there to its endpoint or its equivalence point, where you have the same number of EDTA moles as you have copper moles copper, right? That's going to be your final volume, right? Let's say that final volume is 7.8 mils, right? Let's just say that final volume is 7.8 milliliters. Okay, so that's where it stops here. And just remember, equivalence point and endpoint is the same thing as that. It's when the color turns to yellow in this case, and then also it also means there's the same number of copper moles as there is moles of EDTA. Okay, so this is an easy calculation to do, right? To figure out how much EDTA actually went into the flask. Final volume, right, which is 7.8 mils, and then initial volume, that was 0 mils, and so now your total volume is just 7.8 mils, right? That's good, right? And so now all you have to do is figure out what the number of moles is of EDTA, right? That was required to get to the endpoint of the copper chloride. And so just like last time, molarity equals number of moles divided by the liters of the solution, right? And just as a reminder, don't forget that big M is molarity for concentration, and little m is, or little mols, is number of moles, right? And so we'll put our concentration of EDTA that we had at the beginning there, right? And then after we convert this to liters, like so, by moving the decimal point 3 places, right? And now we have liters. We can move that number there, right? So right under the number of moles, right? So then our equation then is this, okay? 0.19 molar EDTA equals number of moles of EDTA all divided by 0.0078 liters of EDTA, right? That's good, liters of EDTA. So all you have to do is solve. All you have to do now is solve for this right here, number of moles, and it's as easy as multiplying the concentration times the number of liters, right? And so I'll do that real quick. 0.19 times 0.0078. So I get here the number of moles to be 0.0014 moles of EDTA, right? Good stuff. Good stuff. All right, so that's helpful, right? Because now you can figure out the number of moles of copper that were in the solution, right? That you titrated right here, right? So how do we do that? Well, we start by saying 0.0014 moles of EDTA. And then recall from up here, we have a 1-to-1 molar ratio. So for every 1 mole of EDTA, you get 1 mole of copper. And then you need to figure out how many grams there are of copper. That's how much copper was in there, right? And that's easy because you can say for every 1 mole of copper, you can look on the periodic table, and the periodic table will say that there's 63.5 grams of copper for every mole of copper, right? So go through and cancel all that stuff out there, moles of EDTA with moles of EDTA, mole of copper, and now all you're left with is multiplying 0.0014 times the molecular weight of copper, right? So multiply that. And so I get the number of grams I get is equals 0.094 grams of copper, right? Well, that's cool because now I can figure out how much chloride is in the solution, right, that we started with. Because all I have to do is subtract this number right here from the chloride, right, from the copper chloride that we started with, right? So if there was 0.142 grams of copper chloride, subtracting the amount of copper I came up with will leave me with just what's left over, which is chloride. So 0.142 minus 0.094, and I get 0.048 grams of chloride, right? And so now all I need to do is convert this now, the grams of chloride, to number of moles of chloride, right? So that's easy. I have grams of chloride, and for every 1 mole of chloride, I have 35 grams of chloride, I think. 35.5? I can't remember. Let me look. I forget now. It'd be nice to have a periodic table in my office somewhere, but I don't. There's chlorine. And its molecular weight is, yeah, 35.5. We'll just round up grams. Okay, and that will give us number of moles of chlorine or chloride in the solution. 0.0, sorry, 0.48, right, divided by 35.5. And that actually gives me 0.01, no, sorry, let me say that again, 0.00, write that again, 0.00135 moles of chloride. Okay, Cool, cool. All right. So now that we have the number of moles of copper chloride here, I mean, number of moles of chloride there, right? How many moles do we have of copper? Well, we actually had it up here, right? We went through this calculation right here, the 0.014 moles of EDTA, right? And then for every 1 mole of EDTA, we had 1 mole of copper chloride. But we went a step further here and went ahead and went to the grams of copper chloride right here, right? And that gave us the actual mass of the copper chloride. But if we stopped one step ahead, right there, if we just stopped right there, then we could just get the number of moles of copper chloride, right? And so the 0.0014 moles of EDTA, right, times the 1 mole of copper chloride, cancel out the EDTAs, you get moles of copper chloride. So you get 0.0014 moles of copper. Okay? So if you look at the number of moles of copper you have, it's actually the exact same number of moles of EDTA you have, which makes sense because it's a 1-to-1 molar ratio, right? And it's at 0.0014, and look at the number of moles of chloride you have. It's 0.00135, which is basically what? 0.0014, right? And so what that means then is that you now have the same number of moles of copper as you do chloride, which means it's a 1-to-1 molar ratio between copper and chloride. So your empirical formula here, in this case, is CuCl, right? Which is copper 1 chloride, right? Now you can do this experiment and you can get completely different numbers and you might get copper 2 chloride, right? But with these numbers, you get copper 1 chloride. But the important thing is to be able to compare the number of moles of chloride with the number of moles of copper, and that will tell you what the molar ratio is between copper and chloride, and that will tell you then how much, what the empirical formula is. And so if you were to have, for example, twice as much chloride as you do copper, right, in the number of moles, what that means then is you have copper 2 chloride. But since you have almost the exact same number of copper moles as you do of chloride moles, it's only a 1-to-1 molar ratio, so it's copper 1 chloride. Okay? And let me remind you one more time here, right? I got the number of moles of copper from this dimensional analysis right here, right? And from that dimensional analysis I just circled right there, you can get the number of moles of copper by stopping before you get to grams of copper, right? And just going and doing the conversion between moles of EDTA to moles of copper, right? And so since it's a 1-to-1 molar ratio, then the number of moles of EDTA will equal the number of moles of copper. And then once you get the number of moles of copper, all you have to do is multiply by the molecular weight of the copper, and that gives you the grams of copper. Okay? And you need the grams of copper, right? Because you need to figure out how much of the sample actually had copper in it and how much of the sample had chloride in it, right? And so you actually have to do the calculation for both. And once you get really good, you can do it all in one step like I did here, right? Or you can do it separately. Do one-dimensional analysis where you just go from moles of DDTA to moles of copper, right, to get this number here. And then you can do a second calculation where you go from moles of EDTA to moles of copper to grams of copper, right, and that will give you this number here. But in this problem, you actually need both of them. So you have to either do them both, right, separately, or do them in one step like I just did. Okay? And that's how you figure out the empirical formula of copper chloride by titration. If you have any questions, let me know. Bye.